will present investigation of knocking combustion initiation based on multi-cycle LES. And without further ado, Dave.
Thank you. Good morning, everyone. I'm happy to present today my work of the past years, talking about knocking combustion. But I want to start with schematics of how the regular combustion in an internal combustion engine looks like. We're all aware that in a spark ignition engine, the flame is triggered by the spark. Then we have the turbulent flame propagation, the complete consumption of the fresh fuel-air mixture, and as a result, we have the well-known smooth pressure curve. Now, it's the nature of the internal combustion engine to have cyclic variations, which look like this in experimental investigation, where we have an envelope of pressure traces around the mean pressure. Now, if we want to increase the efficiency, one thing to do is advancing the spark timing. We get a higher mean effective pressure, but in the end, what may appear is single pressure traces where we have pressure oscillation overlaying the general pressure trace, which is called knocking combustion. And since this pressure oscillation have a high risk of danger for the engine, in the end, knocking combustion is a major limit for the efficiency of combustion engines. And with that, of course, it has been and still is part of investigations and research. Schematically, what we know about knocking combustion is that it is always triggered by autoignition events. So the high temperature and pressure in the fresh gas ahead of the flame front leads to the autoignition of the fresh mixture. And then for the case of the knock limit that is investigated here, starting from this autoignition spot, there's the propagation of a pressure wave and a reaction front, and those travel at different speeds. And what is detectable in the pressure trace in the end is the movement of the pressure wave through the cylinder. Now, what my study is looking at, we are looking at the cause and effect chain. So we investigated how the flow affects the combustion and how the combustion in the end affects the autoignition. So this is the overall topic of this talk. For this, of course, we have an experimental reference engine. It's a full metal engine that is investigated in Aachen by our research partners. It's a close to production engine with a given operating point. It's a port fuel injection with stoichiometric mixture. And as a fuel, we are using a TRF, which was designed in a study. So there is a chemical mechanism available specifically for this TRF, which consists of around 500 species and 2,000 reactions, and which is then further on used in the LES. For the results I'm later discussing, I'm focusing mainly on this three planes. So the middle plane, it's shown in red, the tumble plane, blue, and then a horizontal plane. And I will reuse this picture to give an orientation where I'm at in the engine. From the numerical setup, we're doing multi-cycle LES. And then, of course, we need to think about how to design this multi-cycle LES. So in the end, we're starting at exhaust valve. In the exhaust phase, we run a first combustion simulation, use this as the input for a second combustion cycle with a full gas exchange. And then after that, the initialization is completed. And from there on, we just run subsequent cycles and dispose the first two to be sure that we don't have any errors due to initialization. And then to reduce the overall turnaround time, I do this in 3 different threads. And using this methodology in the subsequent talk, I have 18 LES combustion cycles available for further analysis. Coming to the modeling part, so all of this engine simulation is run in our in-house solver TF Motion, which is OpenFOAM based, of course, and where my colleague Andrea Patti invested a lot of work to get all the meshing and the optimization we heard about yesterday running. So my part was mainly to get this TF motion ready to simulate knocking combustion. And what we need here is first a description of the turbulent flame propagation, of course, and then a description of the autoignition, shown here as a green volume in the unburned mixture. For the turbulent combustion model, in the CFD, we use the well-known flamelet assumption that the 3D flame can be approximated by an ensemble of 1D flamelets. We then calculate a bunch of this 1D flamelets with varying the initial conditions to capture the full thermochemical state of the engine operation. Tabulate these 1D flamelets into a database, and then use this reduced order model to access it from the CFD, where we only need to solve transport equations for a limited number of control variables. And of course, here the most important one is the combustion progress variable C, which is closed in this case with an algebraic FSD model. For the turbulent autoignition, there's a second progress variable, the autoignition progress variable, where again a transport equation is solved. And now we need to process this autoignition progress variable further. It is first normalized, and then in the second step, we take into account the turbulent flame propagation and end up with the normalized progress variable CI. And this now can be used to identify the so-called critical volume. So all the CFD cells that are predicted to undergo autoignition. And now with this volume, we can evaluate the critical mass, so the mass of unburned mixture that undergoes autoignition. And this is a key feature of this model, and we will see this value critical mass further when I'm discussing about the results. Now for this transport equation, there's an unclosed term, which is the source term in this case. And of course, we follow a similar approach. We access this source term from a database, and now this additional database is composed of 0D reactor calculations, where we had access to a pre-existing model from our group that was successfully used, where linearization was assumed. Now, as the left plot shows, this approximation by just using the inverse of the autoignition delay time may not be the best use for the operating conditions investigated here. So that's why we adapted this model, and now the source term is determined by the detailed autoignition progress of the autoignition progress variable, and we are able to capture the autoignition characteristics that are relevant for the operating conditions of the engine. Okay, with that, let's come to the results. This is the pressure traces that are relevant for the operation conditions investigated here. We see the regular cyclic variations of the pressure traces around the mean. And if I now overlay this with the 18 LES cycles I have available from my multi-cycle LES, we see that we match both very good in the mean pressure trace, and that additionally the LES is capable to capture a reasonable amount of the cyclic variation, so capturing around 1 to 2 sigma around the mean pressure. So this is combustion, and there of course is the knocking part, and here we are comparing the knock intensity experimentally shown in gray with the critical mass I talked about before, and we see that the LES is capable of capturing cyclic variations both along the x-axis, so in the prediction of the knock onset, as well as on the y-axis, the variations in knock intensity. So globally, our LES is able to capture cyclic variations in combustion and knocking parameters. Now, specifically for this engine, there's also optical data available. So they equipped this full metal engine with an optical spark plug. And now with the 40 channels of this spark plug pointing in the cylinder, they were able to detect the light emission from the auto ignition event and then trace back in which of these observation cones the knocking was happening. Similarly, for the LES, I divided the cylinder in 40 wedges. And now what is plotted here is the critical mass binned to this 40 wedges, first shown for one LES realization. And now if I overlay this for all, the video is not playing. This is set. Let's try it this way. Okay. Now, I must say the agreement is way better than it looks here. So what is expected to show as a video is that, of course, now I have way more data available with the 18 LES cycles. And we see the similar trends that are also apparent in the experiment. So we have a really good agreement that the knock initiation is predicted to be mainly happening between the exhaust valves. So in general, now we have the validation that this LES study is able to predict or to capture the cyclic variations both in the global quantities as well as in this localized information. With that, we used the available data to now look at the cause and effect chain to figure out the interactions between flow, combustion, and auto ignition. I want to start here with the flow, of course, which is what is shown here is the ensemble average field of the velocity at the spark timing. And we see the formation also indicated by the white arrows of the velocity field, the formation of the tumble close to the spark plug. Bringing this in connection to the flame, here's the ensemble average of the combustion progress variable. And we can interpret this as a flame probability. So value of 1 means that all my 18 LES realizations have seen a flame here. If I now overlay this flame probability with at an early flame phase, so at top dead center, with the velocity vectors at the spark timing, we see that the flow, so the tumble, pushes down the early flame towards the piston. So there is a clear interaction between the flow and the flame. For the further analysis, I made use of the Pearson correlation coefficient, where I investigated correlations between two features, X and Y. And I did this for many features, but here I want to focus on the correlations between a combustion feature and an auto ignition feature. And this combustion feature now is based on the flame on the middle plane, and specifically this feature is the flame width on this middle plane at top dead center. And this will be now connected to the critical mass. We already seen this before, so an auto ignition feature. And again, here's some transparency missing. I'm sorry for that. Incompatibility between Mac and Windows. But the main information is there. If we plot the flame width against the critical mass and do some regression, we see that there is a linear trend, so which indicates that a larger flame width at top dead center is correlated to a higher critical mass or a higher knock intensity at the end of the combustion phase. And this is somewhat interesting. So it is further investigated now locally. And what I did now was to calculate this Pearson correlation coefficient, not globally, but locally, so for every CFD cell. And what is shown here is now the correlation between the auto ignition progress variable, CI, and this combustion feature of the flame width. And there's two regions of interest between the exhaust valves in red and then between intake valve 1 and exhaust valve 1. So this is regions that indicate that a variation in the flame width is correlated to a variation in the auto-ignition progress here. And interestingly, similar regions appear if I do the correlation now between the auto-ignition progress and the critical mass. And now with this, with the help of this local correlation analysis, what I did was to compare two realizations of my LES to figure out what is happening here. So these two LES realizations, they show a really similar global combustion progress, and they mainly differ in the two features that we discussed before. So in the early flame width and in the critical mass. And what is plotted here is as a white isoline, the flame front and the auto-ignition progress variable CI, where now this one is colored in a way that only regions that contribute to the critical mass are shown in yellowish colors. And what now can be found is that the fresh mixture in the pockets between the flame front and the cylinder liner show high auto-ignition progress between the exhaust valves. So indicating that almost all of this unburned pocket mixture is undergoing auto-ignition and contributing to the critical mass. While the picture is different for the pockets at the top between intake valve 1 and exhaust valve 1. So here only a minor contribution to the critical mass is visible. So this indicates that the location of these pockets of unburned mixture are determining the critical mass of our combustion. And with the correlations we've seen before, there's the indication that the local distribution of these pockets of unburned mixture is already decided at the early combustion phase. And with that, as a summary, we were able to make use of this multi-cycle LES to investigate correlations between the flow, the combustion, and the auto-ignition, and now have a powerful tool available to make use of for future challenges in regard with the internal combustion engine. And with that, I'm at the end and open to questions.
Thank you, Magnus, for the nice talk. Any questions? Start off, Kari.
Hey, Kari Keskinen from Wärtsilä. Thank you for the very impressive presentation. Regarding your NOC model, I'm really a lot of time thinking about this, the different options.
Maybe you can speak up a bit.
On your NOC model.
There is the microphone.
Cheers. So for the description of your auto-ignition process, you probably spent quite a bit of time thinking about how to do it. I have two parts for my question. First, how easy was it for you to determine meaningful auto-ignition progress variable? And did you try out or consider having some reduced mechanism for the end gas to compare with it? What do you think are the, let's say, relative pros and cons in those approaches?
So as I showed you, this is based on there was a pre-existing model which used the formaldehyde as a precursor species, which did not work for our case now. But determining the auto-ignition progress variable was kind of easy, I would say. I just used the fuel consumption here, so the overall fuel consumption, which works really good and is as continuous, and so all the requirements for the progress variable are fulfilled. In terms of the mechanism, since I'm tabulating, and it's 0G reactor calculations that are going into the tabulation, the size of the mechanism is not a bottleneck for us. So it's overall several thousand of homogeneous reactor calculations. Of course, this takes time, but compared to the calculation time of the LES, of the multi-cycle LES, this is negligible. So, yeah.
And if I continue there, did you ever consider running kind of a reduced mechanism online?
Online? No, we did not do this. But what we see is, so what I tried out was a smaller mechanism for the tabulation, just to try it out. And we saw that this may not work. I mean, the mechanism really needs to be optimized to capture both the laminar flame speed and the auto ignition times. Yeah, relatively well to make use of it.
Yes.
Yeah, interesting work.
Wait for the microphone.
The question, oh, thank you. All right, yeah, Hong and Klaus, nice work. I just want to have a question, clarification about your details of the modeling of you when you do the 0D tabulation of the ignition of end gas. This is a classical Livingood problem. You cannot just determine the ignition event based on the initial condition. You have to integrate over evolution while the end gas is compressing. So I wonder how that part is incorporated in your model.
Yeah, I got the question. So in the end, what we need to assume is that by tabulating enough of these homogeneous reactors, we are able, by lookup to the single homogeneous reactors at the certain state, resemble the overall evolution of the unburned mixture in the CFD. So the tabulation really is based on just the homogeneous reactor calculations with a fixed initial conditions, and then by varying the initial conditions for this homogeneous reactor, and during the tabulation process, we need to make sure that we have the full chemical state put into the tabulation, and then during runtime, over the auto ignition progress variable, we access the results of the single homogeneous reactor calculation, and then we need to assume that, like, the interpolation of several homogeneous reactor calculations based on different initial conditions resembles the development of the onboard mixture and CFD.
If I understand correctly, you are kind of resetting every time step at a local point and look up different 0D data from different initial conditions?
I'm not. So what I transport is the auto ignition progress variable, and I make use of this to access the tabulation.
Okay, I see.
So, and of course I need the other control variables as pressure, as enthalpy, to figure out which point in the table I'm at. So, but like the connection between the homogeneous reactors and the state of the end gas is via the auto ignition progress variable.
I think the Livingood-Wu would be the linear, right? So we don't use the Livingood-Wu.
No.
It's a type of problem, but not the linearized version. So that's important.
Hi, Bart Somers, Eindhoven. In essence, this is just, say, a tabulating approach, right? Do you also connect this to heat release?
No, there's no back coupling to the CFD. So it's a precursor model. Yeah, it's really about predicting of the auto ignition. There's no back coupling.
Can't you combine your laminar flame tabulation with this, and it just decides on its own whether it auto ignites or is propagating?
There has been work on this, which showed that it is not easy to just, like, as you propose, use the auto ignition progress variable and then just set it to burnt, because it works a bit different.
Okay. And another question I had is, how do you treat do you filter these source terms, or do you just say extract them manually, so to say? Is there any PDF or?
No, there's no, at the moment, there's no subgrid scale PDF available, no.
But this was done in Dirk's work that we showed that this has little effect.
Yeah, it doesn't, no. Not so much.
There was one more question down here.
Yeah.
And then I think we have to move
You
on.
have I apologize because I was late. I don't know if you have already explained this, but I would like to ask, how do you compute the filtered source term? I mean, you have a kind of turbulence combustion model, partially stirred reactor, or just compute source term as a function of the filtered variables? Yes, this way.
No.
Okay.
Only for the ignition, right?
Only for the ignition, yeah.
That's only the ignition cursor. So the regular combustion process, of course, has all the bells and whistles you need for a turbulent combustion model. So this is only for the ignition tracer.
So it's handled differently between the combustion progress variable and the auto ignition progress level.
The rest is a flamelet approach based on flame surface density. So, yeah.
Okay, thank you very much. So, I hope I don't butcher the Italian names too much. The next talk is by Francesco.
Yeah, I know. I have to
Just one point. If you do presenter visualization, in the video that will be shared, there will be the video of you, but not the video.
Okay, I can switch back.
Okay, sorry for
No, absolutely no problem. Because I am used to use it. So.
No.
Sorry.
Francesco, I come because I need to fix another problem. Because if you do this, then you lose the sharing.
I'm sorry, Tommaso, I didn't know.
But that's the life of a CFD person, right? You fix one problem after the other.
You fix on when the next comes. It's not so easy now to get back. Okay, then.
Ho già cambiato.
No. Capisco adesso perché. Perché poi cosa fa quando fa visualizzazione?
Non lo sapevo.
Velocità di reazione infinita. Che a quel punto
So his presentation is on CFD simulation of injection processes in open foam, under expanded jets and Lagrangian sprays. So please go ahead.
Thank you for the kind introduction and sorry for this little issue. So basically this presentation is framed within the collaboration of my research group with University of Perugia and the research group of Professor Michele Battistoni. And for the second part of this work with the Aramco Research Center in Detroit. So a little bit of background about what I'm presenting today. So I will talk you, as mentioned, about spray simulation. And today we are working, all of us, many of us, we are working with fuels like hydrogen, methanol, propane, ammonia, new gasoline blends, e-fuels. And all of us face the fact that this spray show different physical behavior. We have to understand if we have to solve or not these under-expanded jets, to understand if these shock structures, shock waves influences the air-fuel mixing, the mixture formation, but also we are injecting in many occasions the fuel in gaseous condition, or also in critical condition. Very often, phase transition is ruled by a kind of very quick, very fast phenomena, which is the flash boiling. So we have to use ad hoc simulation tool, and the purpose of this work is to present our work, what we've developed for simulating this spray. And we know that we can focus our attention in two different areas of the spray. On the near nozzle, and we usually use the Wöhlerian finite volume approach. For sure, we can use spectral elements or other things, but most of the work was done with finite volume methods. We need to, as mentioned, to understand the underlying physics. We need to, for sure, to get a reliable result, limit the numerical dissipation. This is kind of a key requirement. And we need to understand the physics because we, for sure, need to develop kind of reduced order model, low order methods, meta models to be used in a whole engine simulation with the purpose of reducing, obviously, the computational efforts. So for this near nozzle simulation, within the collaboration with the University of Perugia, we are proposing this approach, which is thought for flash boiling transition and to represent flows with strong compressibility effects, which are the ingredient to get a code that is actually capable of handling this kind of flows. We need to use something that is good in terms of fluid properties description, and the University of Perugia developed a real fluid property package within OpenFOAM. We are using it, and we, as you can see, this is for propane. We are getting good representation. But as I mentioned, we need adequate numerics because we have strong compressibility effects. We have these shocks under expanded jets, and we need to limit, as I mentioned, numerical dissipation. As we know from the literature, the best approach would be to use central schemes. Central schemes have an important drawback, and it's the fact that they are not stable in terms of numerics. And so in OpenFOAM, there is an implementation of a flux splitting method for central schemes, which derives from the Rusanov theory. And it's basically the Kurganov-Noel-Petrova scheme. We also implemented it in this multi-phase code together with the other high order methods for temporal integration for the reconstruction of the flow fields on the phases. To complete the overview of the methods we are using, we need to say something about the phase transition, phase change that takes place in a thermal non-equilibrium condition. And we implemented in OpenFOAM the homogeneous relaxation model. We used it because it's widely accepted because it gives quite good results. And this is the name we gave to our solver, Real Central HRM4. So we need to validate this code, this multi-phase compressible with phase transition solver, and we obviously rely on SCN data, which give us so many information. Spray G, all of us know the G2 condition. We have 0.5 bar, 363 Kelvin of temperature, but especially we have X-ray data from Argonne. And this is the grid we obtained from the SCN website, and we performed the last simulation on that. And as you can see, with the let me say a quite small computational effort, we obtain improved results in terms of density maps comparison. This is a density X-ray density map. This is our density map from the CFD simulation, and this is the density profiles across one jet of the spray. And as you can see, we are not so much at 2 millimeter, but 1 millimeter. We are getting very close to what was recorded at Argonne with X-ray. But let's go a little, not behind, but forward. This is the pressure field, the temperature field. Okay, we have a little bit of depressurization among the jets, but it's important to test the code in a condition where we also have under-expanded jets. So we considered always the spray G injector, but a propane injection. And we investigated a subcritical and a supercritical injection of propane. So it means that with injecting at 360 Kelvin, we are injecting a liquid, while if we inject at 390 Kelvin, we are injecting basically a vapor, which is obviously very dense, but it's a vapor. And we are allowed to do this thanks to the real property package. And the rest of the setup, it's almost similar to what we have done for isooctane. And this is the results. We are capable on reproducing the under-expanded jets in this multi-phase flow. This is the supercritical injection. For the subcritical injection, that's an amount of liquid which covers the under-expanded jets. But as you can see, we can observe the spray collapse from this vapor plot. Let's go a little bit on, and this is a three-dimensional visualization of the under-expanded jets. And we can observe the primary shock cells in direction of the nozzle holes. And between two jets, we have a secondary cells. This is important to have a correct representation of the pressure field in this area for this reason. Because as you can see, plotting a pressure profile that is crossing two jets, we can observe that exactly crossing the jet, we have a strong depressurization of obviously of the pressure. And even if we are considering this area on the jet axis, we are below the ambient pressure. And this is, we believe that this is the main reason of the spray collapse. The spray collapses because the internal pressure is lower of what we have outside. You can find the other results on this paper, which was published a few days ago. And let me go on, and let's look at the same problem, the spray simulation, from a different perspective. Something that it's more affordable in terms of computational resources, especially for the industry. We, all of us, know that it's the Lagrangian spray simulation. But another time, we have some issues when we want to simulate flash boiling condition. And we very, very easily end up in flash boiling when we inject methanol, propane, ammonia, these new gasoline blends, when we have early injection condition. So what you have to do, many of us need experience that we have to extremely tuning the breakup model constant. We have to set unreal spray angles. We easily get a droplet sizing which is inaccurate. We cannot catch properly the spray collapse. So it's a tricky field. So, but let's move a step behind. And which are the key models for the a Lagrangian spray representation? Obviously, the phase change model. But today, I'd like to focus our attention on the breakup model. And for that, within the guise of Aramco, and what we have done, I can say that this is what we usually think when we refer to the breakup. The breakup is something that depends on the aerodynamics on the interface between liquid and gas phases. And so basically, it's basically aerodynamic instabilities. But since we are injecting a superheated spray, a superheated liquid, we believe that there's another mechanism that is driven by thermodynamics, which is driven by bubbles that grows within the droplets. And Rayleigh-Plessé equation, it's what we have as the rule of that basically drive the bubble growth. And we finally decided to put these two mechanisms together in a concurrentive way. So basically, this is the primary breakup mechanism, and then we can have aerodynamic breakup mechanism. But let me give you some details about how the breakup model works. The breakup criterion say that we have breakup once the stability grows larger than a characteristic length of the spray, which is basically the liquid film. As you can remember from the previous slide, there is a bubble, and around the bubble there is the liquid film. And when the stability grows larger than this characteristic length, we have breakup. We can control the breakup with this parameter, and with this parameter, we can control the droplet sizing. We can control the bubble growth rate, which derives from the simplified Rayleigh-Plessé equation, and so we account for of that with this other parameter. And as you can see, can control the spray collapse. Finally, we added a radial component to the velocity vector to account of the plum-to-plum interaction, which is a consequence of flash boiling onset. And obviously, this model was developed within OpenFOAM as I mentioned, with the guys of Aramco, but also it's present on LibEyes. Within the collaboration, we have also with the Polyme and ICE group. What we have done in terms of post-processing results, we decided to do something that could be very, very tricky, but we decided not to use just PLV maps, penetration curves, and so on, but we decided to use also density maps acquired from X-ray to validate the approach. We developed a post-processing procedure which combines the Lagrangian and the finite volume results to get the density map from CFT. We exploited this work that Aramco commissioned to Argonne. This is for a 6-hole side-mounted injector. This is obviously a flashballing injection condition, what we consider. But I want to underline the fact that we are not injecting isooctane, but a real gasoline surrogate, which was let me say developed at Aramco. It's a surrogate of U5 gasoline, and this is what we get. Obviously, the setup is. I will be very quick on that because all of us know what are the usual settings. I just want to mention that obviously the effervescent breakup is the FB breakup model, and then for the aerodynamic breakup we use the Rayleigh-Stillwater model. And these are the density maps. As you can see, we achieve a good agreement with the X-ray experiment with our Lagrangian simulation. We can observe that the spray path footprint at 1 millimeter is closely resemble the X-ray experiments. But this is not enough, obviously, because we have to understand what happens downstream in the whole, obviously, for the whole spray morphology. And thanks with another collaboration with STEMS, we have. This is a G2 condition, but we lower the ambient pressure to 0.2 bar. And this is the MEA scattering acquired at Laboratorio SPRAI in Naples. And as you can see, this is isooctane, spray G, as I mentioned. As you can see, we are able to catch the spray collapse and also the penetration curve. As you can see, the plumb cone angle and the plumb direction are basically the nominal one of the spray G. Let me conclude this overview of results with an extract of the latest SCN, because this breakup model is also capable on, it's also dependent, it's also sensible to different fluid properties. And within the latest SCN, both University of L'Aquila and Polyme, we simulated with the effervescent breakup model spray M in M2 condition, we considering methanol and PES20 sprays. And as you can see, also with methanol, the spray morphology is sketched quite well, spray collapse and all of that. And these are instead the penetration curves that both Polyme and Univac obtained to simulate PES20, and this is plumb width. We can see our results are quite promising. So this presentation would give an overview of our activity in the simulation, CFD simulation of spray, fuel spray. The first part regarded the near nozzle finite volume approaches, for simulating near nozzle. We developed a low dissipative code for simulating indeed multi-phase under expanded jets, featuring flux splitting schemes for compressible flows, fluid property package, and the HRM phase change model. This code is quite fast. We believe that we can exploit it to understand the underlying physics of this phenomenon to get simplified models, to understand what we have to solve about underexpanded jets in terms of engine application. And we validate, obviously, the approach with the spray-G data. The second part of this presentation regarded Eulerian Lagrangian approach and our idea of an effervescent breakup model, that it's a different breakup model ruled by thermodynamics. And it actually performed quite well with flash boiling spray, reproducing quite well spray morphology, both in the near nozzle and in the far field. It's capable, this model is capable of reproduce spray collapse without changing spray angles, and is also sensible to the fluid properties. So thank you for your kind attention, and I'm ready to
Okay, questions? Yes, yeah.
Yes. So thanks for the presentation. I have one question. If you go back to the criteria of the breakup for the flash boiling, very nice finally with the game of flash boiling. It's a nice topic. Can you go to yes, that one? I see that using as criteria, the breakup is proportional to the difference of the radius.
Yeah.
So assuming that the length, peripheral is the criteria actually. I see there was in the past some work that they use as breakup criteria, comparison between the bubble volumes with the volume of the original parcel, so that go with the cubic of the bubbles.
Yeah.
I want to hear something more on why these criteria go linearly with the radius instead of cubic of the radius. So just if you give some hint.
Yeah, this is an interesting question. Thanks. So basically, let me go back to the equation. Here we have an instability, which it's a length, not something that is as the dimension of a volume, as the dimension of a length. So for this reason, the first approach is to compare it with a length. And the primary approach, the primary idea one can think at is to compare this instability with what length. This is the length of, and at first thought we believe that we can compare the instabilities. Obviously, there could be other options like the one you were mentioning. So extracting a characteristic length, it must be a length. It cannot be a volume. But we can get it from other consideration, other relations where it compares the volume, and for sure it can be investigated. It can be modified the model. Yeah.
But are you considering that there is one bubble that's grown up in the Rayleigh process, not multiple bubbles that go together? It's one, right?
Yeah, it's kind of, I know, it's kind of a simplification because you have one bubble for each droplet. We thought at this in this way because it's obviously a simplified approach. We can in the reality it's different. No, obviously you have a liquid core, especially in the near nozzle zone, and you have kind of density distribution of bubble, but you have to simplify it to make it working on a Lagrangian code. No,
yeah, sure. Thanks.
You're welcome.
Okay, two more questions, and then I think we move on.
Hey, Karl Kesner from Wärtsilä.
Yeah.
Question about the HRM model that you have in implementation.
Implementation?
Or I mean, is the HRM model that you have, is it, let's say, implementation, is it equal to the, let's say, the original HRM correlation, or have you made some changes?
Okay.
I'm asking because I have some experience and maybe some past issues with that model as well.
Okay. You are referring to the old solver, or in particular to the phase transition model? Because the HRM, as I showed here, it's the phase transition model, but we developed not only the HRM, we developed a complete new solver.
Yes, but yeah, in particular the phase transition.
Okay, about the phase transition, we basically translated in open form the HRM model, which is broadly, widely documented in literature. We know that there are other models. The guys of Argonne developed this mixing driven, something like that model. But as you know, OpenFOAM it's quite flexible on that. We can easily modify one routine, and we can implement different approaches for the phase transition. But honestly speaking, I don't think this is what makes the difference. What makes the difference are these parts and these other parts, because we believe that you have to get the correct numbers for the fluid properties, but at the same time you have to limit numerical diffusion. Otherwise, you won't have this agreement basically. Okay. And in other implementation, in other commercial softwares, let's say, you don't have flux splitting. You don't have flux splitting. You don't have this combination of second order temporal integration. You don't have this representation of also. I didn't mention to go fast, but within the real fluid property package, there is further than the Peng-Robinson equation of state. There are the Chang relation for the dynamic viscosity, and there's a modified Janov relation for CP and CPO, which takes into account the dependency of the specific gates, not only on temperature, but also on pressure. And so this is a combination of these.
Thank you.
You're welcome.
Thank you. Yeah, Benjamin Stadt. I just have a question regarding turbulence, and do you expect that these have effects on flash boiling or maybe on the onset of flash boiling? Because you mentioned diffusion effects and other effects, and all these experiments are typically done in low flow situations where you don't have turbulence. Do you expect any change in engines to comment on this?
Very tough question.
I know.
From a phenomenological point of view, yeah, these are sprays that are studied both experimentally, obviously, from the CFD in a constant volume chambers. So when you put them on an engine with a piston that moves, and maybe the air circulation is completely different because the piston pushes the air. We know what happens in an engine, you know? So the flow field is different. It's obviously different. And especially for that, we need to understand what we have to, let me say, solve, and what we can just model it on or at most neglect it.
But at least I observed in the engine is that you have the strong convection of the turbulent, as you mentioned, that this pushes the spray to a side or this shape changes. But for my experiments, I can't.
Sorry, again.
So you see that the spray is pushed by a convection if you have a strong inflow or topple flow, as you said correctly. But from an experiment, I cannot judge, is it just the flow, the convection, or is it maybe the turbulence itself which modifies maybe the nuclear balloons or anything else? So therefore, I think it's very helpful to have these simulations that you're doing. So if you learn more, please contact me.
Thank you.
Okay, I think we have to move on. So
thank you.
Okay, the next talk is given by Matteo from ITO.
Okay. So good morning, everyone. First of all, thanks for the introduction. Today I'm going to show you the effort that we made to try to classify the effect of turbulent mixing on ignition behavior of spray flames, high pressure spray flames. And first of all, I will try to show the reason behind our work. I do believe everyone is familiar with the engine combustion network. For those who are not, is a consortium of researchers who are trying to create a database, a wide database for of sprays experiments in order to give to us CFD researchers material to validate our models. And in particular, this work is focused on two diesel sprays. Spray A, which is representative of a passenger car nozzle, and the spray D, which is representative of a heavy-duty nozzle. And problem here is that from experiments, as you can see, at 900 Kelvin, spray D ignites later compared to spray A, while at 1100 Kelvin in chamber, it ignites at the same time. So in order to understand the behavior behind these results, we first dig into the non-premix combustion, how non-premix combustion works. I borrowed this very useful image, in my opinion, which shows, which classifies the phases of combustion into a localized lean first stage ignition, after which we do have a low temperature combustion, and in which the time after which we find this low temperature combustion is mainly influenced by the chemical kinetics, as you can imagine. Then we have a turbulent curve flame wave, which is inversely proportional to the scalar dissipation rate, so the rate at which the oxidizer and the fuel are mixing. And then we have the broad reach second stage ignition, after which we do have the onset of a high temperature combustion. And then we have the turbulent flame propagation, which is not important for this work now. So the methods that we use to analyze the problem, first, as a combustion model, we did use the flamelet generated manifold, as the name says, it is a flamelet-based model. Therefore, we do have times of the time scale of the chemical reactions, which are far smaller compared to the time scales of the turbulence acting on the flame. And so we can actually represent the flame as an ensemble of monodimensional flames. In our case, we do use counterflow flames, where we do have a fuel and oxidizer meeting up in the stagnation line and create a flame. And so we can follow the evolution of the flame in the physical space. So we do have all the thermodynamical variables in function of the physical space. Then we can transform these variables in another space, which is the space of the control variables, which can be several. In our case, they are mixture fraction, progress variable, variance of mixture fraction, and the enthalpy. So we do have, at the end, a table where the 3D simulation can retrieve all the thermodynamical variables based on the value of the control variables in the domain. Therefore, in the domain, only the governing equation of the control variables are solved. So as you can imagine, we do have a good, less effort in terms of computational time. Then as far as the turbulence, we do use an LES. In particular, we have the dynamic structure, which differs from the Zmagorsky-based model because the subscript scale tensor is a model based on one equation, which is the equation for the turbulence kinetic energy, and also because Zmagorsky-based model do use a fixed constant that is case dependent, so it cannot be most of the time generalized. While for the dynamic structure, as the name says, this constant is solved on runtime. Then, as mesh and software, we are using OpenFOAM-v7.org version. I'm not boring you with all the schemes and the solvers. We are using second order schemes basically. And what the most important thing to consider is that we are using a very refined mesh. The geometry is classical, traditional for this kind of application. It is a cylindrical shaped mesh divided in two parts. The first one, close to the nozzle, is very refined and does not have any grading cell by cell, while the second part has more grading. The point, the most important point, is that we wanted to have the base size of the mesh, which had to be smaller at all the time than the flamelet, than the thickness of the flame, basically. So we ended up with a 62 micrometers cell size as a base, which led us to a total cell count of 63 million cells, which run on our cluster in 15 hours on 384 cores. And as far as the performance goes, we do evaluate the performance in terms of ignition delay time, lift-off length. Of course, the ignition delay time can be divided in the ignition delay time of the low temperature combustion and high temperature combustion, which are reported here. However, there are no experimental values for low temperature combustion. I mean, there are some, but not this specific. And as you can see in the brackets, there are the experimental values. The model reproduces them quite well, I would say, both in terms of ignition delay time and lift-off length. However, the most important thing to consider is that the model reproduces well the problem that we are dealing with. So at 900 Kelvin, indeed, spray D is igniting later than spray A, while at 1100, no, this behavior is not seen. We do use this approach on the right, which is the IXT plots, which are basically radially integrated mixture fraction of the CH2O that you see in green and the OH in red along the spray path. We do take these planes and we do integrate these mass fractions to get an idea or about where the ignition happens. And then we can get finally to the scalar dissipation rate influence, because the whole point is how much the scalar dissipation rate influences these combustion phases. And I know these plots are really complicated, but basically what we worked on first was a classification of the scalar dissipation rate. There's no objective, there's no traditional definition of scalar dissipation rate. So what we did was just taking two criteria. The first one is the conditionally averaged the scalar dissipation rate based on equivalence ratio and the average over all the cases, and you can see the double brackets. And for low and moderate, then we took the average of the scalar dissipation rate, maximum scalar dissipation rate over all the cases, and for high and intense, and we took a percentages basically. So we do have low, moderate, high, and intense scalar dissipation rate in those color. And in these plots, there are these scalar dissipation rate influences basically on the CH2O formaldehyde mass fraction to see where the peaks of formaldehyde is in terms of equivalence ratio and scalar dissipation rate intensity. What we can say is that at 900 Kelvin, spray D, as you can see, shows peak of high and intense scalar dissipation rate, and which are not present at 1100 Kelvin, where we do have only low and moderate scalar dissipation rate, peaks of CH2O in low and moderate scalar dissipation rate. This, of course, are snapshot right before the low temperature combustion onset. So we can say, since the first snapshots at 900 Kelvin for spray D shows this scalar dissipation rate intensities, we can say that these classes of scalar dissipation rate do not favor the ignition, and that is why spray D is showing a later ignition of onset of the low temperature combustion. Why at 1100 Kelvin the behaviors are really similar. That's why the times are really similar as well. Then we have the same kind of approach for the high temperature combustion, and we can see that the effect of that high and intense scalar dissipation rate on spray D at 900 Kelvin is there and is influencing also the high temperature combustion, since we do see those peaks there, but also important to notice is that they are moved towards richer equivalence ratios. And this is not good for the high temperature combustion. It's not well influenced. The onset is retarded even more if you make the maths there. Indeed, the high temperature combustion onset is even further compared to the difference between the low temperature combustion onsets. And while again at 1100 Kelvin the behaviors are really similar actually, and the onset times are really close. And finally, what we did was taking 3 time steps I'm showing here on the bottom the spray A time steps at which we took this snapshot that you see on the top, where we see that CH2O during the evolution, these time steps are right after low temperature combustion in the middle, and then right after high temperature combustion. We do see that CH2O has a peak at the lean mixture fraction, then moves towards richer condition, while OH, which in the beginning follows, if you see the dots in yellow for OH, in the beginning follows the peak of CH2O, and then instead of moving as CH2O does towards richer equivalence ratios, moves back to kind of richer condition, but not as rich as CH2O does. Therefore, finally, the conclusions. First of all, the low temperature combustions occur with low and moderate levels of scalar dissipation rate in lean mixtures, and at 900 Kelvin spray D, in spray D, the formaldehyde is found in less favorable condition. That is why it ignites later, basically. And all cases show peaks of OH with low, moderate, and high levels of scalar dissipation rate in rich mixture. But the most important thing is that the combustion onset at all temperatures is not favored by an intense level of scalar dissipation rate. And that's all. Thank you for your attention.
Thank you for the talk. Now, questions. Anyone?
Thank you, very nice presentation. Just a curiosity, I saw that you use a crystal accurate scheme in time or?
In time, yes. Because we found it to be a little bit more stable for this kind of application. But we tried also a second order. It is usable, but not always. Since we are starting these large jobs on the cluster, we wanted to be really sure that worked and didn't crash.
Another question was, you don't solve for the variance of the progress variable?
Yeah, we don't.
So not usually this kind of parameter are based on also on the.
Well, there are works talking about the importance of variance of progress variables, but all the time they are, it's a second order importance, let's say. The most important one is the variance of mixture fraction that has to be included, of course, to take into account the turbulence density interaction, and therefore to not get to a too large table, because those are large tables we are talking about. We decided to discard them.
Thank you.
Any further questions? Maybe then I ask a more general question. What is, in your opinion, something sort of underappreciated in complexity when you do these simulations?
What do you mean?
So something that maybe doesn't come across, or that's very difficult to do, but usually people don't talk about it or don't present it because it's, I don't know.
I mean, for this kind of applications, I do believe that the first thing is it is very difficult to run these kind of cases, because as you can imagine, it's very large. And besides, the scalar dissipation rate is kind of not mystery, but I would say it's kind of difficult to grasp the sense of all this. That's the point. But if you really want to get why, to appreciate why these two spray flames are igniting at different times, you don't have any other choice, in my opinion. You gotta get into the real detail.
Okay. Thank you. Then I guess we have a coffee break now.
Exactly.
Back here at 11. And please, the spray and modeling people part 2 upload.